The example that we had where we had the people who were doing sales and the people who are doing production, and we're trying to figure out the probability that they would be in one or the other. That was an example of trying to use that addition rule for when we have mutually exclusive events. Okay. Mutually exclusive really just means that we have two events that really can't occur at the same time. So, two events are said to be mutually exclusive if it is impossible for both events to occur. So, they can't occur at the same time. So, in that data, if we had somebody who was working production, they weren't working in service and they weren't working in sales, they were just working in one field. Another example of this is if I roll a die and I have event A is that I come up with three, but event B is I come up with an even number. There's no way that I'm going to roll an event where I get a three and an even number. So we can't roll a three and an even number at the same time or simultaneously. And then we're talking about in just one roll. So I can't have just one roll where I get a three and an even number. That what makes it mutually exclusive. I can't have both things happen in one event. If I toss a fair coin and I toss a heads and event B is toss a tails, I can't toss a coin once and it comes up both. So I can't have a toss B heads and tails at the same time. Or another one, maybe it makes a little more sense. So we choose a person at random. Event A is that person is biologically male, and event B is that person is pregnant. You can't have somebody who is born male be pregnant. So this would be another mutually exclusive event. You can't have a pregnant male human anyway. Yes, you can as seahorses, but as far as humans go, you're not going to have a pregnant male, at least not yet. So this is what we mean by mutually exclusive. They just can't happen at the same time. So suppose that a college student is chosen at random, determine whether events A and B are mutually exclusive. So we split it into two groups here. So here, event A, the student is older than 21 years old. Event B, the student is taking statistics. So are those mutually exclusive? If I'm older than 21, am I forbidden from taking statistics? No. This case is not mutually exclusive. And that's because someone can be over 21 and take statistics. So B, or the other side here, event A and B, A is that the student is an only child, and then the event B, the student has a brother. Yes, this is mutually exclusive. I don't think we have to think about it too much. If you're an only child, an only child can't have a brother. So if you have two events that can't possibly occur at the same time, that's what's going to make it mutually exclusive. And usually I see the struggle with this is just remembering mutually exclusive means they can't occur at the same time. So we kind of already saw this, but in events A and B, if events A and B are mutually exclusive, then this event, probability A and B, is going to be zero. The probability of being a single child and having an older brother is 0. You can't have that happen. This leads to a simplification of the addition rule. So if we have mutually exclusive events A and B, then the probability of A or B is the probability of A plus the probability of B. So addition rule for mutually exclusive events. Let me do a little adjusting here. So given a 52 card deck, what is the probability of drawing a jack of spades or a heart? 0 in on this. So if we're looking for a jack of spades and a heart, let me move this just a little bit. This card right here is going to be my jack of spades. And these are going to be my hearts. This is mutually exclusive. So jack of spades and hearts are mutually exclusive. That means I do the probability of a jack of spades or drawing a heart. Really, all I'm looking at is the probability that I have a jack of spades plus the probability that I have a heart. That's all I have to look at because there is no place they overlap. I don't have to worry about finding a card that is a heart and a jack of spades. So we have 1 out of 52 cards is a jack of spades. We have 13 out of 52 cards are going to be a heart. We have 14 out of 52 cards, or 7 out of 26, or what is 7 out of 26? Or 0.269. So 26.9% probability that you would actually draw a jack of spades or a heart randomly from a deck of cards. So in recent years of the Olympic Games, a total of 11,544 athletes participated. Of the 554 representing the United States, 314 representing Canada, yay, it's pie, 125 representing Mexico. What's the probability that an Olympic athlete chosen at random is representing the US or Canada? So you can't represent both countries at the same time. So representing US and Canada is mutually exclusive. So the probability that somebody represents the US or Canada is basically the probability that they represent the US plus the probability they represent Canada. So we have 554 out of 11,544 for the US. We have 114 out of 11,544 for Canada. So that is going to be 868 out of 11,544 that represent US and Canada. So the probability that we randomly choose somebody that represent the US or Canada that is going to be 0.0. Oh no, that's right. 0.075. The chance that a random athlete would actually represent somebody from the United States or Canada is about 7.5%. Try to get that fit in there just a little better. So in a statistics class of 45 students, 11 got a final grade of an A, 22 got a final grade of B, and 8 got a final grade of C. What is the probability that a randomly chosen student would have an A or a B? Once again, you can't get a grade of an A and a B simultaneously on a final or for a final grade. You only have one grade. So the probability of an A or a B, we can just go, okay, so we got, was it 11 A's and 22 B's out of 45 students? So that's 33 out of 45. So that's 0.73. So there was a 73% chance that somebody in the statistics class would have got a or a B. The probability got an A, B, or C, so they pass and they can transfer it. Once again, there's no overlap to worry about here. So we got 11 A's, 22 B's, and we got 8 C's. So we got 41 out of 45. So this is 91% of the class. So 91% of the class get a passing grade, a passing transferring grade, put that way.